In this video, I'm going to be showing you how to determine the structure of an organic molecule after being given its mass spectra, its IR spectrum, its proton NMR spectrum, and its carbon-14 NMR spectrum. So to start off, we're going to be looking at its mass spectrum, which I have pulled up right here. We were given the chemical formula, and that is C8H19N, which I have written at the top. The total mass of that is 129 grams per mole. Although for this video we were given the chemical formula, the whole purpose of the mass spectrum is to help people determine the formulas of unknown chemicals. So I'm going to show you on this mass spectrum how we could have possibly determined that C8H19N is the correct chemical formula. One of the first things we want to look for is whether the parent ion is even or odd. So for this mass spectrum, the parent ion is 129. That's the molecular weight of it. And what you can determine from whether or not it's even or odd is whether or not it has a nitrogen in it. If it is odd, then it will have a nitrogen in it. And if it's even, then it usually does not have a nitrogen. And because our parent ion has a molecular weight that is odd, we know that that's how we got this nitrogen. Really, the only other thing that we can get from this mass spectrum is that there's a lot of alkanes. This big peak at 86 is indicative of a hexane. The peak at 57 is indicative of a butane. The peak at 44 is indicative of propane. The peak at 28 is indicative of ethane. And the peak at the 18 and 17 mark is indicative of methane. And these are all different alkanes that can be detected by the mass spectrometer. So knowing that we have a nitrogen in the molecule and knowing that the rest of the molecule is just going to be carbon-carbon bonds with hydrogens attached, which are alkanes, we would be able to do math to determine the final chemical formula of the molecule. So now we're going to look at the IR absorption spectrum for this molecule. One of the first things we notice about the IR spectrum is this big dip right here around 2900. And what that tells us is that there is an alkyl carbon-hydrogen stretch, which is indicative of an alkane carbon-hydrogen bond. And that definitely goes with the information that we got from the mass spectrum, because the mass spectrum, as we remember, showed us a lot of different alkane groups that could have been broken down, and this IR goes hand in hand with that. We also have another little dip right here around 3400, and that could be indicative of a nitrogen to hydrogen stretching bond. The last thing I want to point out in this is the dip right here around 1100, which could possibly be indicative of a carbon to nitrogen stretch. So what this IR spectrum tells us is that there's going to definitely be a lot of carbon to carbon alkanes, and there's also going to be a hydrogen attached to the nitrogen, and there will also be a carbon to nitrogen bond at the very least. So next we're going to take a look at the proton NMR for this molecule. The first thing we notice is that there are 5 signals, and that is 1 right here, and then there's 3 right in there, and 1 really big one right there. The next thing that we can grasp from looking at this is the number of hydrogens in each of these signals. First off though, the total number of signals that there are pretty much tells you how many different kinds of protons there are in the molecule. So knowing that there are 5 different signals on the spectrum, we know that there are going to be 5 different kinds of protons in this molecule. Now the numbers above each signal tell us how many protons are going to be in that type. So starting right here, in this type of proton, there's going to be 4 of the same type. And the same goes for this one. There's going to be 4 of that type of proton, 4 of that type of proton, 1 of that type of proton, and 6 of this type of proton. So from this proton NMR, one of the first things I noticed is that there's a very large peak with 6 hydrogens right around the 0.9 range. One thing that is indicative of is a CH3 attached to some sort of other molecule. However, since there are 6 hydrogens, there will probably be 2 CH3s. So from here we can start drawing the molecule. So I will draw 2 separate CH3s. One of the main other things that I noticed is that there is a shift right there that only has 1 hydrogen. And from what we know that we gathered from the mass spec and the IR, we know that somewhere in this molecule there's going to be a nitrogen bonded to a hydrogen. So we know that that 1 hydrogen noted in this proton NMR will probably belong to the nitrogen. So because we only have 1 nitrogen that's bonded to the hydrogen, and we know that the nitrogen's not going to have a charge on it, we can assume that it's going to be making 2 more bonds. Because nitrogen has 5 valence electrons, so it would make 1 bond here, 1 bond there, 1 bond to hydrogen, which would give it 3, and then it will have 2 valence electrons. So because we know that nitrogen is going to be making 2 separate bonds, and we know from the IR that the only functional group that we're going to have on here besides the nitrogen bonded to the hydrogen is going to be an alkane, then it's safe to assume that the rest of this molecule is just going to consist of carbons bonded together with hydrogens attached. So based on what we already know from this proton NMR, this peak right here with the 6 hydrogens is going to be this group right here on the end. We know that this group right here with 1 hydrogen is going to be this. But now we also have 3 groups with 4 hydrogens that we haven't identified yet. So one thing that we know is that saturated alkanes are typically found on a proton NMR spectrum between 0.5 and 2. Now, of the groups that we have left, there's only 1 group that does not have a saturated alkane, and that is this group right here, because they are both bonded to nitrogen. And because this peak is outside of the 0.5 to 2 range that the saturated alkanes are under, these 4 hydrogens belong to this group. Therefore, these 2 remaining peaks with 4 hydrogens each belong to this group and this group. Although it appears as though we figured out what the structure is for our molecule, we're still going to look at the carbon-13 NMR. And you can tell what the different kinds of protons are because each group has a different neighbor. This group right here has a CH2 neighbor to the right. This group here has CH3 neighbor to the left and a CH2 to the right. This group here has CH2 to the left and a CH2 to the right. This group here has a CH2 to the left and nitrogens to the right. And this group has only a CH2 to the left. So each group of protons has different neighbors, and that's what makes them different. And that's why they each have different peaks on the proton NMR. Now we can use the carbon-13 NMR to verify our structure. In carbon-13 NMR, the CH3 bonds are typically found at about 13.9 or 13.7. So these CH3 bonds are represented by this signal right here. The second CH2 that's attached to the CH3 is usually represented by a signal in the low 20s. So that CH2 would be represented by that signal. The third CH2 is typically represented by a line in the low 30s, and so that would be represented by this signal right here. And that leaves this type of carbon to be represented by this signal. So after using mass spec to verify the formula, IR to find the functional groups, and proton and carbon-13 NMR to figure out the structure by determining the types of hydrogen and carbons, we determined this to be the final molecule for this C8H19N structure.